In this video, I'd like to run through several examples from our current MathXL homework. This is homework number 4, and it covers exponent properties. Now, before we get into exponent properties, there are just two questions meant to warm you up here to the math. If we're faced with this expression that needs to be simplified, let's remind ourselves that we must combine like terms. So 8x and 19x are like terms that will be combined, and negative 8 and positive 11 are like terms that need to be combined. So 8 take away 19x leaves us with negative 11x, and negative 8 plus 11 leaves us with a positive 3, and we've simplified that expression. Similarly, 10y plus 16y minus 13y will leave us with 13y's. And no other like terms combined with this negative 9. So we'll report this as 13y minus 9. Now as we move on from here, you'll start to see actual law of exponent questions. And hopefully by now you're pretty comfortable with the rules. However, if you're not, you can always go back to the notes from earlier in the week and reference these law of exponents. The summary of the laws are listed here on the left-hand side, as well as these explanations in the second box. This column in the middle provides a numeric or concrete example of how to apply the law. And if you're more of a verbal type, the verbal description is also shown over here on the right-hand side. So by referencing these laws of exponents, we should be able to simplify the expressions as they're presented to us here in MathXL. So in number 3, what I notice is that we have a negative exponent, and I recall that a negative exponent will be changed to a positive exponent as long as we move it to the bottom of a fraction. Or if it already was in the bottom of a fraction, that means we could bring it to the top of a fraction. So this would be okay as a solution, but we can do better because we can actually evaluate what 4 to the third power is. So I'm not thinking about the fraction right now, I'm just trying to evaluate 4 to the third power, and that means 4 times itself 3 times in a row, and that leaves us with 64. So I would say that 4 to the negative third power simplifies to 1 over 64. In number 4, we have an x to the fourth term and a y to the negative second term. Now these two are unlike one another, so they cannot be combined together, but I do notice a negative exponent with this second term. This positive exponent here, there's nothing really we can do to simplify that. That's pretty good as it is. But this negative exponent, we're going to apply the same rule as before. So I'll remind you that we could treat these as fractions if we needed to, and it's going to be quite helpful in this particular case. Oops. Negative 2 over 1. Because we know from the negative power rule that this expression can be moved to the denominator of a fraction as long as we change its power to positive. And we're not going to change this one, so that has to stay where it is in the top of a fraction. So this helps me to realize that x to the fourth remains in the numerator of a fraction, while y squared gets moved to the bottom of the fraction. And now we've written this equivalent expression with now only positive exponents. This expression is the same as the original, and we only have positive exponents. Now this is a multiple choice question, so in this case, after doing the work, I would select option B. In number 5, we see something that's similar. We should recognize that this negative exponent will turn to a positive exponent if I bring it to the top of a fraction. And we have x over 1 with y cubed over 1. We leave these 1's here as a placeholder after terms move in case we need to reference them later. So we have x times y cubed over 1, but anything divided by 1 is just that original item. So it's safe to call this one xy cubed. And again, on MathXL, this is a multiple choice question. So after having done the work, we can now report this as a solution. We have 2 more examples involving negative exponents. So I would suggest that you try these on your own. Pause the video now and resume playback in a moment to check your work. I would say that example 6 is pretty straightforward. There shouldn't be any surprises here. In number 7, it's a bit interesting that we have a negative number that's being raised to a negative power. So let's just remind ourselves that this negative number being raised to a positive power in the denominator would be the same. Those two are equivalent expressions. And I chose to emphasize this here, that the number negative 5 is being raised to the power of 4. So it's the number negative 5 that multiplies by itself 4 times in a row. And the result of 4 negatives multiplying together does produce a positive, and 5 times itself 4 times in a row is 625. So negative 5 times itself 4 times in a row is positive 625. For the next few examples, we're referencing what happens when we multiply two terms that have common bases. Now in our notes, I tried to emphasize that here. If you're looking at the description, it says to multiply two powers of the same number, add the exponents. And I wanted to stress that number in this case is referencing the base of the exponent. The base is the bottom number, while the exponent is the small number at the top. So certainly these two have a common base, and there is a multiplication symbol here indicating that the 7 and this 7 and this 7 are multiplying together. So since the bases multiply, they stay the same, and the rule states that we should add our exponents together. And so 5 plus 9 is 14, so this would reduce to 7 to the 14th power. Now we could reach for a calculator and evaluate 7 to the 14th power, but the instructions... So the 7 to the 14th power could be evaluated, but the instructions in MathXL do say to write our answer in exponential notation with positive exponents. So I do believe this is the result that they're looking for on MathXL. For the next example, we can follow much the same pattern. The two bases are the same, and when the bases are the same and they multiply together, we add the exponents. So here to say that this is 6 to the 16th power is appropriate. Now in problem 10, it gets to be a bit interesting because we have three bases that are all the same and that are being multiplied together. So the same rule still applies here. We can add the exponents together. Now the first thing that I'll note is that with no exponent written on this last term, we'll assume that there's a value of 1 in its place. And so the end result is going to be 5 to the power of 4 plus negative 6 plus 1. Now we know that 4 plus negative 6 is the same as 4 minus 6. So 4 minus 6 plus 1 is negative 1, and I would report 5 to the negative first power as my answer. Now we should be a bit hesitant with this because we're not used to reporting our answer with negative exponents. So I would be prepared if MathXL doesn't accept this answer or an answer similar to this to go ahead and rewrite this as 1 over 5 to the first power or just 1 over 5. Now again, the instructions say just to type your answer using exponential notation, so I think they will accept this. There's no indication that it has to have a positive exponent, like the next example does say non-negative powers. So this one should be accepted. But in the event that it's not, go ahead and apply your exponent rules to rewrite it. For number 11, I don't believe there are any surprises there, so I've got y to the 11th in this example. In number 12, we should note that the number negative 3 and the number 2 are coefficients that multiply together, so we should find out what negative 3 times 2 is first, and then we can treat the bases as x. So the base of this exponent is x, and the base of this exponent is x as well. The number 2 and the number negative 3 are not bases at all. They are coefficients that must be multiplied together. Now the exponents of the bases of the letter x do get added together, so 2 plus 8 is what we need to accomplish for that expression. And the number negative 3 times 2 is negative 6. So I like negative 6 times x to the power of 10 as the solution here. And here again, the instructions from MathXL say to use positive exponents only, which we've done. The negative 6 is okay because that's a coefficient, it's not an exponent. The exponent was positive 10. It's interesting to me that sometimes they'll say that our base must be raised to a non-negative power, and sometimes they'll say that we have to use positive exponents. But those two expressions are synonymous, so be prepared for that in case you see them. Now I would approach 13 much the same way. I would multiply my coefficients together because the coefficients, and this one's got an assumed 1, the coefficients are not part of the exponents themselves, they're in front of the exponents, so those get multiplied together. Then the exponents can be added, and the reason why they can be added is because the bases are all the same, and if you didn't notice, there's an implied multiplication symbol in between each. So when the bases multiply, the exponents add, and we end up with negative 15z to the 22nd power. Moving on from here, we start to see examples of a power-to-power rule. This was law number 3 and 4, and I suppose we can even lump in number 5 here, 3, 4, and 5 from our list. And that stated that if there's a single base that's being raised to a power, so x to the second power here, and that group is being raised to another power, power of 4 in this case, then the rule this time is to multiply the bases together. And we end up with x to the 8th power in this example. Number 15 also follows that rule. We have a to the negative 3rd power that's being raised to the 2nd power. So I would say that this is a to the negative 6th power. Taking note that the solution should report only positive exponents, I'm going to move that to the denominator of a fraction and change the sign to a positive result. And we've got 1 over a to the negative 6th power. Now some of you may recognize that negative exponent first and choose to rewrite it this way. 1 over a to the 3rd power raised to the power of 2, which is perfectly fine because law number 5 says that if I see a fraction with an exponent on the exterior, then we apply that to both, the numerator and the denominator. Now 1 to the 2nd power, or 1 squared, is still 1, and a to the 3rd power squared, a to the 3rd power squared. Well, we've kind of already thought about that one already. We know that the 3 has to multiply by 2, and we end up with a to the 6th power as well. So either technique, if used appropriately, will lead you to the correct and final answer. And there should be no surprises with problem like number 16. Now we're getting close to the end, and with number 17 and 18 we notice that fractions are involved. And I wouldn't be too concerned about them because this is just a reminder that when two bases are being divided, we can actually subtract their exponents. So I'm going to treat this as the common base of 7 with the exponent of 7 minus 4, which is just 7 to the 3rd power. And since this is a multiple choice, we will choose option A because the expression can be simplified, and we will report 7 to the 3rd power as the simplified result. With number 18, I would do the exact same thing. The common base g is being divided, so both of these exponents have a base of g. So I know that the result requires us to subtract the exponents. Now you do have to be really careful here. Negative 2 minus negative 6 is really the same as negative 2 plus 6. The two subtraction symbols or minus symbols cancel each other out. And this end result becomes g to the positive 4th power, and I would report that as g to the 4th. Now, if the subtraction did lead us to a negative result, we would go one step further and report our answer as a positive exponent. However, algebraically speaking, this does reduce to a positive exponent, so we'll leave it as it is. And that actually brings up another point here. I suppose some of you might have seen it this way with the negative exponents, that you'd like to correct the negative exponents immediately. Well, remember that a negative exponent can be pushed to the denominator of a fraction, and then it turns to a positive exponent. And similarly, if the negative exponent exists in the denominator, it can be pushed to the numerator, and it too will turn positive. So if we made that our first step and then recognized common bases where the exponents must subtract, you'll also notice that the solution does end up being g to the fourth power. So again, either technique, when applied appropriately, will lead you to the exact same and final answer. Now, with 19 through 21, we start to combine some of these rules. Now, what I like to do, as long as I recognize that there's a series of multiplication across the top and the bottom of the fraction, I like to treat these as almost two separate fractions. So I have x to the 9th power over x to the 7th, and that result will be multiplied by y to the 6th power over y to the 6th power. And if I treat those as two separate fractions, then I think answering each one is a little bit more manageable. So I'll focus on this one on the left here, and the first thing that we get, or first thing that I see, is that we have a common base that's being divided. So the exponents must be subtracted. That's going to look like x squared to me. When I look at the second combination, well, I notice that y to the 6th is being divided by y to the 6th, and so that's a number divided by itself. That should be equal to 1. Some of you may recognize this as a division with common bases, which is fine, and a division with common bases requires us to subtract the exponents, so 6 minus 6 is 0. We also have another rule that says that any base to the power of 0 must be equal to 1. So we end up getting x squared times 1 again anyway, and any number times 1 is that number by itself. So I would report that this expression, when simplified, is just x squared. Why don't you use those same techniques and try this one on your own? You can pause the video now and resume playback in a moment to check your work. After separating into three fractions that multiply together, I recognize that 54 divided by 6, or 54 over 6, reduces to 9 over 1, or just the number 9. X cubed divided by x squared, when we subtract the exponents, leaves us with x to the first power. And y to the fourth divided by y leaves us with y to the third power. It's not necessary that we report x to the first power. We can simply record that as x, and so I like this final answer, 9 times x times y to the third power. And for our final example, we'll again split this up into pieces. So 4 cubed divided by 4 to the 6th times m to the 6th over m to the 9th times t to the 8th divided by t to the negative 6th. So me personally, I like to eliminate the fractions first, so I'll do that by subtracting the exponents when the bases are common. So I now have 4 to the negative third power, m to the negative third power, and t to the 14th power. 8 minus negative 6 is positive 14. I'll also note that a negative exponent can be written as a positive exponent as long as we change the position of the exponent from top to the bottom or bottom to the top of the fraction. So in these first two examples, to change the exponents to positive 3's, we move them to the denominator of a fraction. And t to the 14th is already positive, so that's technically sitting on the top of the fraction. Now I recognize that 4 cubed is a numerical value, so I'll go ahead and simplify that. That's 64. 4 times itself 3 times in a row is 64. M cubed cannot be simplified. Now those two elements still remain in the bottom of a fraction, while t to the 14th stays on the top. So the end result that we get here is the combination of all three of these fractions. And again, if it's not abundantly clear, we're just reminding ourselves now that when multiplying fractions, we can multiply straight across, numerators with numerators, denominators with denominators. And we're left with t to the 14th power from the collection of numerators and 64m cubed in the denominator as a collection of the denominators. So I hope this video helps. I know that your examples for MathXL aren't the same as mine, but the techniques should be very similar. Thanks for watching.